At the core of every phone, computer, and digital device on Earth is a single mechanical requirement: the ability to control the flow of electrons. For the first half of the 20th century, engineers did this using vacuum tubes, or valves. These were glass bulbs that essentially shot a stream of electrons through an empty vacuum, moving them from a glowing hot filament called a cathode over to an anode. But these tubes had strict physical limits. They were fragile, required dangerously high voltages to operate, generated massive amounts of heat, and burned out constantly. Building a functional computer meant wiring thousands of these together, resulting in machines that took up the size of a whole room. To make circuits smaller, faster, and more reliable, scientists needed to ditch the fragile glass and the glowing filaments. They needed a way to direct traffic entirely inside a solid block of material. The leading candidates to pull this off were elemental semiconductors, specifically pure silicon. There was just one glaring issue. At room temperature, pure silicon is terrible at conducting electricity. If you try to pass a current through it, almost nothing happens, rendering it practically useless for building a circuit. If we zoom in to the atomic level, we can see why. The silicon atoms are locked together in a perfect, rigid crystal lattice. Every single outermost electron is trapped in a tight covalent bond with its neighbor. A covalent bond is just a chemical link where two atoms share their electrons to stay stable. Because every electron is busy holding the physical structure together, there are no free particles left to carry an electrical charge. Physicists in the mid-20th century were stuck with a puzzle. They had to figure out how to force this perfectly stable, completely locked-down crystal to conduct electricity on command, without melting it down or destroying its structural integrity. The engineering fix they developed is a process called doping. It involves taking perfectly pure silicon and deliberately injecting foreign impurity atoms directly into the lattice. Engineers add these dopants at a ratio of only a few parts per million. It is the chemical equivalent of dropping a single grain of salt into a swimming pool. To make it work, there is a strict physical rule. The foreign dopant atom has to be nearly the exact same size as the silicon atom it is replacing. That way, it slips into the existing grid without bending or warping the crystal's overall shape. This precise substitution transforms the pure silicon into an extrinsic semiconductor. The material remains entirely solid, but its ability to conduct electricity multiplies by orders of magnitude. We swap one silicon atom for a pentavalent element, like phosphorus, which has 5 valence electrons. 4 lock into perfect bonds with surrounding silicon neighbors. The loosely held 5th electron absorbs ambient thermal energy, breaks away entirely, and roams freely through the crystal lattice. Because this specific impurity donates a free particle to the system, it's called a donor impurity. And since the majority of the electrical current in this material is now carried by these newly freed, negatively charged electrons, physicists classify this as an N-type semiconductor. Instead of a 5-electron atom, we insert a trivalent atom, like boron, with 3 valence electrons. It forms 3 bonds, leaving an empty vacancy, a hole. As neighboring electrons shift to fill the nearest void, the hole effectively travels through the solid material. We call this an acceptor impurity, because it accepts an electron from the lattice. Since these mobile holes act exactly like actual particles carrying a positive charge, a silicon crystal doped this way is known as a p-type semiconductor. By mastering these 2 techniques, engineers created 2 distinct materials. On one side, an N-type solid swarming with free negative electrons. On the other, a p-type solid swarming with mobile positive holes. When you physically merge them to create a p-n junction, wandering electrons from the N side cross the border to fill holes on the p side. This establishes a permanent internal barrier, a depletion region, that perfectly dictates the direction electrons can flow. This solid-state junction did exactly what the bulky vacuum tubes did, but without the heat, the high voltage, or the empty space. It became the foundational building block for all modern diodes and transistors. By swapping out just a few atoms in a piece of silicon, we learned to direct the flow of electricity on a microscopic scale. That precise material arrangement is the invisible architecture powering every computer, smartphone, and digital screen on Earth.